You pull out your phone, make a move in a chess app, and before your finger leaves the screen, the computer delivers a checkmate. That instant reaction feels like absolute magic. But beneath that split-second decision lies a massive, invisible mathematical burden. If a machine tries to find the best move using a blind search, it has to evaluate every single possible option on the board, and then every possible response to that option, treating every branching path equally. Actions that feel incredibly simple to human beings quickly unravel into impossibly dense calculations when forced through this kind of rigid processing. This diagram illustrates a trap called a combinatorial explosion. A single choice branches into three paths, which instantly branch into three more, multiplying outward within a dozen moves. This web expands so aggressively that the dead-end possibilities outnumber the atoms in the universe. Even a modern supercomputer attempting to evaluate every one of these branches equally would require thousands of years to calculate a single simple move. Yet your phone just beat you in 3 milliseconds. How did the algorithm escape the trap of infinite mathematics? Imagine you are a hiker stranded at an intersection on a foggy mountain peak. Multiple distinct trails branch out in front of you, but the heavy fog reduces your visibility to near zero. A blind search strategy demands that you walk all the way down every single path, descending deep into the valleys below just to see where they eventually lead. You would exhaust massive amounts of physical energy and time exploring routes that clearly head in the wrong direction. Instead of handing you a complete map, we replace it with a compass and a dial-based altimeter. Together, these tools estimate the summit's location. You adopt a highly efficient rule of thumb. Without knowing the exact route, you simply eliminate any trail that goes downward, choosing only paths that consistently gain elevation. This altimeter functions exactly like an AI's internal logic. You can successfully move toward your goal without ever knowing the entire path in advance. The computer science equivalent of that altimeter is the heuristic function, which is written as h of n. It's an algorithmic shortcut calculating the estimated distance to a goal. In navigation, it simply draws a straight vector line to your destination. Or in chess, the heuristic estimates victory by scoring variables like piece values, positional control, and king safety. Algorithms like A-star search use these scores to instantly prune the decision tree, discarding massive branches of bad choices without fully calculating them. A heuristic search solves the combinatorial explosion not by processing data faster, but by aggressively ignoring useless information. Because these algorithms rely on estimated guesses rather than exhaustive mapping, they cannot mathematically guarantee a flawless perfect solution every single time. This animated scale illustrates a strict compromise in artificial intelligence, the balance between making a decision fast enough to be useful and holding out for absolute perfection. Forcing an algorithm to find the single, objectively perfect answer is a computational death sentence. The machine would freeze for millennia trying to double-check an infinite string of variables. By intentionally sacrificing the guarantee of absolute perfection, the heuristic search makes problem-solving physically feasible in real time. It is tempting to assume that a powerful AI is simply a machine that can calculate every single possibility in the universe. But raw computational horsepower means absolutely nothing if the algorithm lacks a sense of direction. True intelligence, whether in human cognition or machine learning, relies heavily on knowing exactly what information to ignore. By trusting in educated guesses, heuristic search provides artificial intelligence with the sharp, decisive direction required to navigate our complex world.